Dear students, today's topic is enthalpy, specific heats and PMM1. So now if we consider a closed system and this closed system is receiving some quantity of heat which is Q from the surroundings and it is delivering some quantity of W, that is the work done, and this work done is by the system. And if we consider this work done as a displacement or PDV work, so we can write that this W is equals to integration of PDV as we have learned in the previous lesson. So the first law of thermodynamics can be written in this case like this, that Q122 equals to U2 minus U1 plus integration of PDV. So what is enthalpy? According to the thermodynamic, the expression of enthalpy is equals to H equals to U plus PV, where H is the enthalpy and U is the internal energy, P is the pressure and V is the volume. So if we divide the whole equation with mass, then we get this the small h equals to small u plus P into small v, where small h is the specific enthalpy, small u is the specific internal energy and small v is the specific volume. So now if we consider a closed system which is drawing some heat Q and which is delivering some work W, and let's consider that work is a displacement type of work or PDV work and the work is performed as constant pressure, and for this the system is changing its states from 1 to 2. So from the first law of thermodynamics, in this case we can write the equation like this, that Q122 equals to U2 minus U1 plus integration of PDV for 1 to 2. So when pressure is constant, in this case we can write the integration of PDV as P into V2 minus V1, and the equation looks like this. And now we can say that Q12 equals to U2 plus P2 V2 minus U1 plus P1 V1. So we know that the expression of enthalpy H equals to U plus PV. So U2 plus P2 V2 can be replaced as H2 and U1 plus P1 V1 can be replaced as H1. So H2 minus H1 can be written as dH, which is nothing but the change in enthalpy or difference in enthalpy for the change of state. Now what is specific heat? So from the definition of specific heat in thermodynamics, we can say that it is the ratio of quantity of heat required to raise the temperature of a body by 1 degree to that required to raise the temperature of an equal mass of water by 1 degree. Now if we consider a mass of dm, where we can say that some amount of heat which is dq is delivering to that mass, by which the temperature of that system is raises to dt. So from the specific heat at constant volume, by definition we can write the equation of Cv like this, and from the first law of thermodynamics we can say that the dq equals to du plus pdv, and if we divide the equation with respect to per unit mass, then we will find that dq by dm equals to d of small u plus p into d of small v. And if the volume remains constant, that means in case of constant volume the equation becomes like this. So now if we put this value of dq dm at constant volume in the expression of specific heat at constant volume, we will find that the equation becomes like this, that is the du by dt at constant volume, the definition of Cv. So in this case we can say that the specific heat of any substance at constant volume, which is Cv, is defined as the rate of change of specific internal energy with respect to temperature when the volume is held constant. And if we consider the specific heat at constant pressure, which is Cv, by definition we can write the equation like this. And from the first law we can write that dq by dm, that means if we divide the first law, or if we write the first law with respect to unit mass basis, we will find that. And for that, the dq dm when P equals to constant, we will get that the dH at constant pressure. So now if we put this value of dq dm in this equation of Cp, we will get the value of Cp is nothing but dH by dt at constant pressure, which means that the specific heat at constant pressure of any substance, which is Cp, is defined as the rate of change of enthalpy with respect to temperature when the pressure is held constant. Now, what is the energy of an isolated system? Let's first know what is isolated system. An isolated system is one in which there is no interaction of system with the surroundings with means of heat transfer and work transfer. So for an isolated system we can write that the dq, that is the amount of heat transfer, is 0, and also the amount of work transfer is 0. So from the first law, for any isolated system we can write that dE equals to 0. So we can say that the energy or the internal energy of an isolated system is constant. Now come to the perpetual motion machine of first kind. The first law states that the general principle of the conservation of energy, that is, an energy is neither created nor destroyed, but only gets transformed from one form to another. So there can be no machine which would continuously supply mechanical work without some other form of energy disappearing simultaneously. Such a fictitious machine is called a perpetual motion machine of first kind, or in brief we can say PMM1. So a PMM1 is thus impossible.